Now let's take a look at the multinomial logic regression. This content is not covered by the textbook, but it's an extension that is very useful for you to know, especially if your project involves a dependent variable that is a dummy with multiple levels. By now, we know that if the dependent variable is binary, we can either use a probit or a logic model. But what if the dependent variable is a dummy with multiple levels? The answer is using a multinomial logistic regression. Multinomial logistic regression is often used to help predict a decision. For example, which candidate will a person vote for, given particular demographic characteristics? Which product will the consumers choose, given their purchasing history, etc. In this class example, we will use the data set of 200 students and a host of different variables, such as the program type, which consists of general, academic, vacation, and their socioeconomic status, low, middle, high, and writing score, to predict what is the effect of their socioeconomic status and the writing score on the program choice. The R packages you need to estimate multinomial logic regression are NNet and Foreign. The dataset used for this example can be downloaded using this link here. You can access the full link in our Markdown file of this module. The relevel function allows you to set the reference level for the dependent variable. This way, you can customize how you want your dependent variable to be shown in the regression. In this case, we chose the reference point to be academic. The command for estimating multinomial logic regression is multinom. You will regress your customized dependent variable, proc2, on the independent variable, socioeconomic status, and writing score. Let's look at the specification of this model in greater detail. The multinomial logic regression used in this example is shown here. On the left-hand side of the model, we have the log odds of attending a general program versus an academic program. Odds is another name for a relative probability. In this case, using the probability of attending the general program divided by the probability of attending the academic program gives us the odds of attending the general program versus the academic program. On the right-hand side of the model, we have the specification that is equivalent of a linear multivariable regression. So even though the name of this model is called multinomial logic regression, the right-hand side of this model is actually linear. Now let's look at the output of this regression. Even though we're only estimating one regression, the output gives us two different regression results. The dependent variable in the first column is the log of odds of attending general versus academic program. The dependent variable in the second column is the log odds of attending a vocational versus academic program. Recall that you set the academic program as a reference point in R, and that's why academic program lies in the denominator of the log odds, and it is not shown in the regression output. Since the right-hand side of the model is linear, we can attempt to interpret these numbers as marginal effects of X and Y. For instance, how do you interpret this coefficient of negative 0.533? This coefficient means that by going from the lower class to the middle class, the log of odds of being in a general versus academic program will decrease by 0.533, holding everything else constant. Note that when you interpret this coefficient, it doesn't have a unit. Why? Because the dependent variable is a log odds, which doesn't have a unit. You say this interpretation doesn't make a whole lot of sense. How do we think of the change in the log of odds? And you would be completely correct. This interpretation is not intuitive at all. And that's why we're exponentiating both sides to convert the log odds into odds using this line of command in R. This command is a generic function in R to exponentiate the coefficients of a regression. After this transformation, we now have the odds of general versus academic on the left-hand side and the dot products on the right-hand side. Fitting these results to the Stargazer function, now the estimates are much easier to interpret. For instance, now you can interpret 0.587 as when a student goes from lower to middle class, he or she is 58.7% more likely to be in a general program than an academic program. Does this mean the student is more likely or less likely to be enrolled in a general program as comparing to before? Now, you take a second to think about this. Pause this video now and ponder about it. I will tell you the answer once you resume playing. Since the coefficients of this model is not additive, but multiplicative, therefore you will use 0.587, which is the whole thing here, when SES middle is equal to 1, times the intercept of 17.326, which is the whole thing here. The intercept now measures the mean of the odds of attending a general versus an academic program for the lower class. Therefore, when you use 0.587 times the intercept of 17.326, the odds of attending a general program versus an academic program actually decrease as compared to before. Decreased by how much? Decreased by 1 minus 58.7%, or 41% lower. You can think of this as before the odds was 100%, but now you're multiplying 100% by 0.587, and therefore the odds is 41% lower. In this module, we first went over 3 different types of model to fit a binary data. There are linear probability model, probit, and logit models. On the left-hand side, they all measure the conditional probability of y equals to 1 given x. On the right-hand side, the linear probability model has a linear specification. The right-hand side of the probit and logit models are given by the CDF of normal and logistic distributions. Moreover, probit and logit are estimated using MLEs. In large samples, MLEs have very good properties. They are unbiased, consistent, and efficient. Additionally, they are normally distributed. This means that we can test on these coefficients as usual. If the dependent variable has more than 2 values, then we use the multinomial logit regression to describe the multinomial data. To make the interpretation easier, we need to convert the log odds to odds by exponentiating both sides of the model.